everyone. I'm Erin Majerowitz, and I will be the moderator for this session. I'd like to start by thanking you for joining us for our presentation. This presentation is the modular architecture for resilient, extensible satellite or small satellites with Mr. Chuck Claggett. Before I begin, I'd like to ask everyone to please turn off their cameras and mute their microphones. We will be recording this session, and it will be available in our media gallery. I placed the link in the chat, so you can access that anytime tomorrow. If you have a question during the presentation, please type it in the chat and I will ask it to Mr. Claggett. He will be sharing a screen and won't be able to see the questions as they come in. We will also be having a Q&A session at the end of this presentation, and you can ask your question by either typing it in the chat or raising your hand. If you do raise your hand, please wait until called upon to ask your question out loud. And without further ado, I'd like to introduce our speaker. Mr. Claggett is presently the branch head of the Guidance, Navigation, and Control Hardware Group at NASA Goddard Space Flight Center. He received his Bachelor's of Science degree in Mechanical Engineering from the University of Maryland in 1983. In his early career, he worked on the Spartan and SMEX programs, developing ACS systems and components. His most notable accomplishments during this time period was the development of custom reaction wheels for the SWAS mission. Mr. Claggett received a patent for his reaction wheel design, successfully licensed and commercialized this reaction wheel to industry, and was selected for NASA Invention of the Year in 1998. In 2013, Mr. Claggett led a Goddard initiative to produce a Class D mission implementation document to provide overall guidance in developing a better, lower cost missions, and including those in the small sat category. Mr. Claggett recently went on special assignment to become project manager for developing Goddard's first 6U CubeSat called Dillinger. The mission was successfully deployed into orbit on November 20th, 2017 from the International Space Station. And with that, I'd like to turn it over to you, Chuck.
Hey, do you hear me?
Yes.
Okay, good. Thank you. On this, I just want to let everybody know that Robin Ripley was originally going to present this. She was unable to, and so I'm filling in. So I may not be able to answer some of the questions, perhaps, but we'll see. I know Robin worked hard putting this together, and I'd like to still thank her for all her efforts. So we'll go from there. So again, this is about a modular architecture that we're developing at Goddard to help work with our small sat missions, and we're going to show you sort of some of our what we're trying to do and some of the hardware we're developing. So right now, from one of our motivations for us is that we feel, of course, we know the small sat market is evolving. Of course, we all see that it's happening pretty fast. But the options for, CubeSat offer inexpensive options that can be scaled to ESPA-class. And I have a problem here. Wait a minute. I can't solve it. Okay. So, it offers up these options, but then, of course, the traditional aerospace market offers solutions for small sats, but, at a much higher robustness and reliability, but at a higher price. So we feel at Goddard, and I think also other agencies and other places and people we talk to, other users feel that there's kind of a gap between these two, the traditional end and the CubeSat end. And we're trying to find a way to sort of develop hardware that's a little bit more reliable for types of missions we like to do, the longer durations, the harsher environments, and things like that, but still at a more moderate price point that like the CubeSats, but not as, of course, not as low as that. So we were trying to find this middle ground here, if you want to call it. And so that's what we're attempting to do. And so, trading off, cost, reliability against, robustness and stuff. So that it's quite a challenge to do that. So what's driving us is, of course, we want this modular architecture to help achieve our SmallSat science goals, harsh environments, long life, affordability. We took an effort to survey our science codes, our scientists, and with an attempt to understand their needs, the different range of capabilities that need to be addressed, to develop an architecture and requirements that would drive our bus architecture concept, and then from there, then internally try to then develop these components, the ones that we feel that we need to produce, as well as we're looking also what we can leverage from industry as well. So so anyway, so we have developed an architecture, and let's see here. So here's the architecture, basically. I think nothing here will be overly surprising, but basically we have, a CNDH board and another interface board that helps interface in all the peripheral components. We've also went with a kind of dual processor approach where we have a high-end processing unit that can do a lot of these high-end specialty things that we wanted to do, and we'll go over some of that a little bit later. And so this way we can, of course, do the ACS systems. We can also act as a processor for the instruments. So we're trying to, of course, merge all this stuff together, share the resources stuff to help shrink down the swap of the whole system. And at the same time, trading off the quality of the parts versus cost, and also doing things in the architecture to help reduce and minimize potential faults that could occur, or make the system more resilient to issues and problems. Of course, be able to patch the code from the ground, etc. So so that's what this architecture basically is, and of course you can add things prop to it if you want. Some things are in our architecture concept is, of course, some things are customizable because every mission needs different needs. So we're trying to kind of blend and balance between having a core set of hardware versus having flexibility in it to accommodate the variety of types of mission needs that are out there. So to carry this further, there's some of the things we have, we were addressing, the mechanical, the thermal, electrical and software. But I think the main thing I want to put on this page is you'll notice that even though we have these variety of pieces here for maybe a more traditional complete bus, you can also take these pieces and assemble them into different configurations, depending on if you want to be an instrument process as an instrument processor, if you just want to use it for instrument application only for like a larger SmallSat category. If you want to make a more high rel CubeSat over a typical LEO mission, these components will be a little bit more rad tolerant and things like that. So you could package it that way, or you could just be a more moderate to lower cost SmallSat configuration for the whole entire setup. So we're also trying to use a lot of commercial. We try to have standard interfaces that allow us to also use commercial components and other other standard things out there. Like 422 interfaces. I think we have SpaceWire in there. I think some of these may be listed later. So, and SPIs, stuff like that. So there's a variety of things. So we can accommodate various, sensor and actuator components, other peripheral special devices that we need, or sensors for the instruments or whatever. Okay, so under the reliability, the way we kind of built the reliability was built around the CNDH. Of course, it stands as a standalone board, but the idea was we would pair it up with, with a high-end processor that maybe is not as rad hard, but it's rad tolerant. And meanwhile, if it got upset, the rad hard CNDH board would keep operating, would reset the system, monitor the system, and make sure it's it continues to operate through, you know, any kind of radiation hits or detect other problems, stuff like that. So that's sort of how we built most of the reliability in terms of from radiation is done around the CNDH, and then it's the monitor for the rest of the system. And so that way the rest of the system could use somewhat less robust components to help still make it more resilient overall that way. Here's a performance chart. This is where I'm not really the best person about processors, but basically you can see where our high-end processors is the Kintec Ultra Scale being used, and I believe our CNDH is here on this RTG4, and so but you get an idea of sense of performance differences between them, as well as compared to some of the other standard processors. Rad-Hard processors have been used up to now in other mission applications. So just give you a sense of perspective here. Oops, what happened here? Oh, I had those here. Okay, there you go. There's the CNDH and the high-end processor. So here is, I'm not going to get too much detail here, but here's the hardware. Fundamentally, the CNDH is, all these are like, I think 1Us are referred to, I think, as electrical card sizes. So, and which is like a cross section of a 1U CubeSat. So that's roughly what the board sizes are here. Here's some basic things. Here's a list of all the different interfaces we have in it. There's CAN, there's SPI. Yeah, I'm not, like I said, I'm not an electrical person here. So anyway, but that's here available in the in this development here. Then this is an auxiliary card that goes with it. It brings you some A to Ds and D to A's. We also have a GPS unit that can be put onto the board as well. Optional daughter cards. So this allows us to interface in a lot of peripheral devices through this, and so that's its main function. Here's the Space Cube Mini, as we refer to it, 3.0 Mini. This is the high performance card. Again, you see it's the same card size slice, and you can see here's some basic specs on it. Again, there's if you guys want more detailed information or have more questions about this, we'll have to refer you to some other people. Or they may be online, they can help answer it today. Anyway, this is a derivative. This is like an advancement of other previous Space Cube work that's been done. Some people may be familiar with it. Space Cube is an ongoing development that's extended multiple years, and this is their latest version that's being produced, and this is its capabilities. So next, okay. The Nav Cube Mini, some people may be familiar with. We also have a high altitude GPS receiver called Navigator. That's also, we're working on shrinking down into use the mini Space Cube Mini form factor. We daughter it up with a RF card basically. It's designed to work well the GPS constellation. And so it's earlier versions of it flew on the MMS mission, a GPS mission, a GPM mission, sorry, and there's other applications that it's been used on. So and of course we're adding in the newer constellations like Galloway and stuff to also be in this design. So. Okay, and then we are trying to, as part of the overall effort to, of the very compact integrated bus concept. Of course, we're also doing a software-defined radio based off of the Mini as well. And of course, the idea is you put in the frequency, the RF card you need to give you the frequency band you're looking for. And of course, it's compatible with all the NASA networks. So this is being developed as well. So, but all the stuff is all kind of interdependent upon each other and tightly integrated to help reduce the swap of the overall system. So we're sharing the resources of the processors across all the subsystems and things like that. Let's see. Whoops, I skipped some here. Yeah, okay. Another key area courses are core flight system software. Again, some people may be familiar with that. Been around a while, but it's part of this system, and it's fairly mature. It's used on a lot of Class B, A through D missions, as well as we've been using on the CubeSats. And it's it's structured and format. Again, I'm not a software person, but it's done in such a way where it's got different layers to it, and then basically the top layer, what happens is, as a user, you mostly, if you brought a new component to the bus design, you just write an app to interface that component in, and then if you conform to the interface to the software, then you basically it'll seamlessly operate with it, and meanwhile you gain all the benefits of the core system, which is allows you to patch code from the ground, to upload new capability and software if you want, to diagnostics and fault detection and correction, and all that stuff is there. So it's a complete software system. So anyway, just to kind of wrap this up, and then we can get to questions and stuff, is that of course MARA is a modular solution with reliability, normally seen missions with a swap of smaller missions. That's our goal, and I think we're achieving it from so far. MARA is designed to be flexible, accommodate commercial and other components, and of course these are and also the main thing I think I want everybody to understand is that all the stuff that we're doing ourselves directly can be commercialized to, anybody wants to license it out, they can do that. And of course, they need to contact the commercialization office. I forget, I'm not sure that's really their name. I think they got a different name. But anyway, Eric McGill is the person to contact there. And if you have more detailed questions about a lot of the electronics and the hardware, you need to contact Robin. Her information is here as well. So I think at that point, I guess we could open up to questions, and I'm not sure how I'm supposed to get those.
If you have a question, you can either raise your hand or type your question in the chat.
I gotta bring that up.
And we will also put all of those email addresses in the chat as well. Our first question comes from Darren. And the question is, you don't specifically mention a power system. Can you expound on what you are planning on using?
Yes. We are going to be leveraging off of a commercial product. We're going to have it somewhat customized for our architecture, but it will be a commercial product that we would purchase and use in this architecture, but designed to work with our architecture.
What is the timeline for development of these systems?
They are presently being developed now. We are probably, it depends on the subsystem or the boards. I shouldn't say subsystems necessarily. They vary, but probably overall, maybe around TR level 5. We're trying to achieve 6, hopefully by the end of this year. But of course, COVID's making that difficult. But the hardware is either some of the hardware exists, like CNDH board already exists. A lot of the other stuff is under board layouts, and they're also leveraging previous designs. So, but like I say, we're actively doing it now.
What about power consumption? Can it be used in CubeSats?
Yes. Our goal was try to keep the power down so it can be used in CubeSats. So the goal I'm trying to, I was going to say there was, 6U could be pushing it a little bit, maybe. Of course, depends on your power system on the 6U, but for sure 12Us because we felt, because again, I think that should be fairly achievable in a 12U, and some aspects of it in a 6U.
I can expand on that, Chuck, if
Okay,
you want.
go ahead.
So it really depends on what combination of components you want to use. If you're using it for a CubeSat and you're using only the CNDH board, for example, the CNDH is in the order of 2, maybe 3 watts. If you want to use it with a SpaceCube Mini high processing board, that's an FPGA. So it really depends on how much you load on the FPGA. But power consumption could be, from a couple of watts to 10 watts or a little bit more, depending on what you have running on that board. So it really depends on the application, on what boards you want to use. Because since it is a modular architecture, you can pick and choose what aspects of it you want to use.
And we have another question. Are you using any standard for the backplane, such as VNX?
Yes, we're using yes and no. We started by looking at standards, and Space BNX seems like the best fit that we wanted to do, but we couldn't really comply exactly with the VNX standard pin by pin. So we had to do our own allocation of pins to make the architecture work, but the mechanical interfaces and the connectors are similar to VNX or the same as VNX.
We have another question. Any specific component technology gaps you'd like to see developed to further MER's SmallSat capabilities?
Well, yeah, I mean, I don't know if we've really thought about all that yet, but I could say, I think propulsion's an area that I know people are working on it, but I think, again, that's something we haven't heavily delved into yet for ourselves, but I know it's coming. And I mean, people are starting to have those needs for that. We would like to see perhaps some better, I shouldn't say better, but perhaps it's not clear to us some of the ACS components that are available maybe are really built to handle the more, longer duration, more radiation hardened environments we might want to send these CubeSats or SmallSats to, right? So I think there's stuff there. Luis, is there anything else?
Yeah, on the aspect of ACS, like you were talking about spinners, it's something that Goddard is very interested in. And the market right now doesn't offer much for spinners. So that's, star scanners, stuff like that. It's something that we're going to look closely pretty soon. Also, we're in early investments on AI applications, artificial intelligence applications for Mars. So we're
Yes.
starting to invest on those areas and be compatible with Mars and the hardware that we have.
Yeah, we like to work towards being more autonomous with our system. So for operations as well as navigation and everything. So
Yeah, and also we're investing on high throughput not communication, but internal communication, like gigabit type of communication with the instrument to the CNDH board or processing unit, and also mass data storage, fast data storage, so we can do more onboard processing of data and making autonomous decisions. But all of those are in early stages. They're not as implemented as the rest of the bus.
Thank you. And our next question, current Goddard SmallSat missions are primarily 6U at the moment, correct? And since you say this architecture is pushing for 6U, are you moving towards 12U or higher going forward?
well, all of it. So whoops, sorry there. So yeah, I mean, well, again, like Luis said, depending on the hardware complement, yes, we can do 6Us. Just you get more limited, right? but yeah, we are looking at 12Us. We're looking at small sats. I mean, it's, you know, the need is there for us across the board because our science community just, there's lots of different types of instruments. There's different needs. Also, I guess to put out there, when we talk about technology advancements too, is, you know, we're interested in formation flying and constellations for some of our science guys. So it's all there. It's just trying to create a, you know, a starting point to allow us to begin to work in those directions. So, and that's kind of this, what this Mares attempt here is to get us kind of a baseline that's more reliable, a little bit more robust, but also scalable, and you know, we can extend it in all these other concepts that we know the science community has. So.
Yep, and I want to add, Robbie, you're correct. We're moving towards small sats, that's for sure, but we're not abandoning CubeSats and 6Us. We still have proposals out there to do 6U CubeSats, and we're looking very closely at the mission and the mission needs, and depending on what the mission needs, then we make a decision if there's something that we want to go in-house or out-house with our hardware or a vendor entire bus. So it really depends on how challenging the mission is and what is out there. And if the market doesn't offer what we're looking for that mission and we have it in-house, then we may go that route with the Mares architecture. But we're also pushing forward with the small sats. We have right now, I think Gushi and Seth, they're two small sats that we're working on at Goddard.
And going back to the conversation on spinners, can you use a simple sun sensor?
It really depends on the requirements for the pointing knowledge. So the sun sensors are only going to get you so far. If you really want tight knowledge, then you need something like a star tracker, but you start losing your solution the faster you spin. So at the spin rate that we want to spin, the current star trackers don't operate. They can't close on a solution. So we're looking at other ways to obtain very good, you know, star tracker type attitude knowledge while you're spinning.
And our next question, is there some place we can buy these cards?
Not yet.
Yeah, not yet. We are very interested in, I mean, there's companies interested, and if there's any other companies you know that are interested, feel free to contact us and Eric McGill, and we can work on a plan for commercializing the boards. But no, right now, you can't get them in the market yet.
And I did put the contact information, all of the email addresses that are currently on the slide right now in the chat. That way it's easier for you to copy and paste it if you would like to contact any of those points of contact, either for engineering or commercialization. That would be licensing and partnerships.
And just for clarity for people, Luis is the other person who's been talking with me here. His name is down here, so, for reference.
Yes. Oh, and
Are there any other questions?
I want to mention another possibility for using this system would be, of course, contacting us, and you know, if you're working on a proposal, we can do a partnership or something like that. We can be part of the project.
Right.
What is the overall radiation tolerance of the high performance compute element?
Unfortunately, I don't have it in front of me, and Robin will be the one with most of that knowledge. I don't think she's connected. Yeah, I don't want to give you the wrong number. So feel free to contact Robin directly to her email, unless James Fraction or someone else from the team is here that can talk about it. I mean, James can talk about the CNDH, but I'm not sure about the high processing.
And Sergio asked about partnerships if it's only in the US. So there are global partnerships that NASA can embark in. It's a conversation that you would have to have with Eric McGill to get the ins and outs of what can and can't be done with a global partnership. Our next question is, what processor architecture is used in the Connect's ultra scale?
Yeah, I'm sorry. That's another good question for Robin.
Yeah.
But on that one, I know on the Kintex Ultra scale, of course, we're using is purely an FPGA, so we're running a soft core in it as well.
Yeah, I think that's the comment the next person just made.
Yep.
ARM
I think
is the
they're
next
asking
question,
what
ARM.
soft core we
Yeah,
using.
it's a microblaze. Yep, exactly. Paul got it. It's a proprietary soft core for the Kintex Ultra scale and the whole Kintex line. And then, of course, the soft core is running our CFS software as well as the CNDH board. The CNDH board was on RTG4 with a Leon 3 soft core running CFS.
Are there any other questions?
And I wanted to mention something about the partnership outside of the US. I think, I don't know if what you were talking about was partnerships mainly in terms of the technology, but in terms of missions, I think there has been some international agreements for developing a mission in which each country brings something to the table, and those are possible too. I don't know if that's through Eric, but we can definitely point you in the right direction if you contact us if you're interested in that.
Yes, that would also be through Eric. So any global partnerships or domestic partnerships, as well as tech transfer and licensing opportunities. Eric would be the main point of contact.
Okay,
Can you
perfect.
show the performance slide again?
Yep. I was just waiting until we got.
And then the next question, did you have any other IP cores implemented in the Kintex? You do something specific?
Yeah, I'm trying to look in the attendees list to see if I see someone else, but
Yeah, now do something. What's the last part? I don't understand. Do something specific. I don't.
so James Fraction, I see you're connected. Do you know about the IP cores on the Ultra scale? I know you worked on the RTG4, but do you happen to know that?
Okay, I think you get a hold of Robin, I guess. So, but I know,
Yeah.
I know what you mean by doing something specific. I mean, like our GPS work we're trying to do would actually run within the implementation of whatever we do in the Kintex. So if you look for applications like that.
Yeah, so definitely the microblaze doesn't take the entire Kintex Ultra scale fabric. So the intent is, since the Ultra scale has a pretty big fabric on the FPGA, we are using our GPS, the radio, and other applications are using those resources for those purposes. And that's one way that we're reducing the swap, is by combining functionality and using the SpaceCube Mini to do most of the digital processing for those applications.
And Louise, James is on, but his microphone is not working at the moment. And he said that he can't speak for the IP cores implemented in the Mini.
Okay, thank you.
Do you know why you did not choose a Zing UltraScale Plus with embedded hardcore processors? They have much higher performance than a microblaze-based solution.
I don't know. I'm sure they had reasons. I mean, it could be a variety of things. I know sometimes those hardcore processors that are embedded may not really be radiation, not very radiation tolerant. Perhaps that might be one reason they're not doing that. So.
Is there any information on latch up sensitivity?
And you have to get to Robin with that. I'm sure there is, because they've flown. Well, I don't know if they've flown this one yet or not, but they may have some information on that.
Are there analog inputs?
Yes, pretty sure. The CNDH side.
Yeah, there's a bunch of DACs and
It probably
ADDs.
go to, where is it at? It's probably say there's current source voltage, well, A to D, DDAs. You can handle thermistor interfaces. Got some heater circuits. Yeah, so there's stuff.
Are there any other questions?
Okay.
Well, thank you so much for your time today, and thank you, Chuck, for your presentation. Oh, we do have a couple more questions coming in. Is the C and DH processor single or dual core? I'm not familiar with the RTG4.
Oh.
Yeah, unfortunately, James is the one to answer that question, and his
Well,
microphone's not working.
He might be able to send in a message and tell us. I don't remember. This is
Single core.
Single. That's what I thought. I didn't want to quite say it, but I thought so. Okay. There was another question, right?
Do you plan to use Exilic, I'm not sure if I'm saying that right, UltraScale Plus slash 16nm FPGAs in the future?
It may be considered in the future. It might have been considered now. Robin will be the one to talk about that. I think it was considered now, but for some reason we decided not to go with it. I know the other board that we have developed for CubeSats in conjunction with the Trek, the Trek board that a lot of people know, that one is using the Xilinx chip that has both FPGA and processor, so they're definitely aware of that. So yeah, again, Robin will be the best person for that. Yeah, and James saying that Robin, it's going to be logging in soon, so we may be able to get some of those answers soon. So stay tuned.
Are there any additional questions?
Robin's going to log on and answer some questions. Okay.
We've had some great questions coming in today.
Yeah, I see one. What vendors did we look at for the EPS components?
Yeah, I'm not sure I should be advertising. So.
Yeah, it's nasty. We could get into trouble by advertising or recommending specific vendors.
And Robin is about to log on to answer some of the questions. She should be on. Oh, it looks like she just joined us. So we'll let her get her microphone connected and she can answer some of the questions that came up.
That's fine. I see the person about the power cord. Yeah, no, we are actively working with a company to make sure it works with our system. So that is happening. So there is going to be a power system.
And we have familiarity with the company and the power system because we're using it on other Goddard missions.
Yeah,
so it's just minor changes
version of it, right? But.
Yeah, so it's just minor changes to the EPS they already have.
Hey Chuck, can you hear me?
I can hear you.
I understand there were some questions about the mini.
Well, you didn't have to necessarily dial in the answer. So what was the What were the questions again that came up? Going back here.
Yeah, one of them, Robin, was did you consider using the Xilinx UltraScale Plus that has the processing in addition to the FPGA?
Or
So we're actually using that on the 3.0, which is a larger board. And it looks like Alessandro's on, and he would be able to answer that in more detail.
They also want to know why you did not choose the, I don't even pronounce it, the ZYNQ Ultra Scale Plus for the hardcore processor.
That's the question I asked. So
Okay.
is the Plus bigger and we couldn't fit it on the Mini? Is that one of the reasons?
Yeah, Alessandro, are you connected through audio? It looks like he's still getting on.
While he connects, we do have another question.
Okay.
51/5000, Space VPX recommends some connector in the standard, is the question and comment.
Yeah, Robin, I was mentioning that we're not conforming exactly with the Space VPX standard because we have our own pinouts for the connectors, but we're using a similar, mechanical and electrical interface with the connectors.
But is it the same connector that the VPNX standard has we're using?
Yeah, we have our own pinouts, but we're using the same connector.
All right, so physically it's the same connector. Okay, just a slightly different pinout. Okay.
Yeah, so I guess the question is if VPX does actually recommend a standard for the connectors, and the answer is yes, right?
Yes. Yeah, they did.
And actually, Robin, is a family, right? Because you can there's like 100 pin, 200 pin, 400 pin
Yeah,
version.
there's a bunch of different connector sizes. We are using the 400 pin on many of the boards in Mares. There is also a 200. Believe the 80 pin option is being used by the nav cube card, the GPS card, and there's also like a 200 that we have. Like 400 and 200 are the ones we kind of have standard pinouts for, but there are other options in that family.
And in the comments, it says in the daughter card and BKP for this form factor.
Yeah, we're using that connector for everything on the backplane and the daughter cards. Yes.
And we have another question. How do you handle the mechanical strain on the connector due to the use of swag lock fasteners?
Page lock.
Yeah, we have a process in which we measure and we put shims as needed to make sure that we get the connector exactly where it needs to go.
Well, yeah, we do some alignment of the board to the, and then also we just make sure the, and then one side of that swage lock is the controlled interface, right? So it's just how you design it.
We have another question. What is the overall radiation tolerance and latch-up accessibility of the high-performance compute model?
That was the other question.
So Alessandro, are you in now? Can you answer that one and the other one?
Sorry, there's a question about the Kintex Ultra Scale device.
Yeah.
Radiation
Can you address
performance?
the radiation one first, and then the ultra scale?
Yeah, so I mean, there have been published papers already on the radiation performance of the Kintex Ultra Scale. It is latch-up immune and has a high TID. The SEU performance is better than the previous generation of commercial Xilinx FPGAs, like the V5 commercial. And then we implement various radiation mitigation techniques through scrubbing and through, as needed, TMR and other options.
Yeah, and the other question was for the Mini, why using the Kintex Ultra Scale the Kintex Ultra Scale and not the Plus version that has also processing in addition to the FPGA. Saying that you're using that version on the 3, but then the 3 Mini, we went with the regular one, not the Plus. Can you talk about that trait?
Yeah, so on the 3.0, we use both devices. We have the real estate where we can actually accommodate both. There are radiation results that you would probably need to talk to Xilinx about specifically that make the Kintex Ultra Scale, not the Plus, but the Ultra Scale, more attractive across a variety of different mission environments. So Geo and others. It's also what Xilinx is, what they're behind or what they're pushing as their space grade device.
Okay, so reliability is one of the main ones.
Yeah.
Yep. Thank you.
How do you implement power distribution within the backplane? Is it bus or point to point?
I think it's bust, right, Luis?
Robin, do you want to take on that one? So, yeah, we do have point to point and we have bus too. We have both. But Robin, do you want to talk a little bit more about
Yeah,
that?
I mean, it's bust. I mean, we have to use a lot of pins out to the backplane to carry the same voltage, but we have planes on the backplane for power, and we're not doing point to point, as far as I know.
And that brings us to the end of our time for this session. I'd like to thank everyone for joining in and answering questions, and also for your participation in this session. You will be able to access the recording tomorrow in our media gallery. And we did place the contact information for both Robin, Luis, and Eric in the chat. I'd like to thank you and encourage you guys all to attend some of our later sessions, both today and tomorrow. All of our events are listed in the events section of our website. So thanks again and have a wonderful afternoon.
Thank you, Aaron.
Yep, thank you.